Hello, in this video we are continuing our discussion of section 6.6 on improper integrals. Specifically in the second day of the lecture, we are talking about improper integrals that have function values that become infinite somewhere in the range that you're integrating over. So this would be infinite integrand ranges. So what this basically means is that you have a vertical asymptote. So you need to see if you can find vertical asymptotes of your functions that you're integrating. The unfortunate thing about this second type of improper integral is that it is much harder to spot than the first type. The first type, you have either positive infinity or negative infinity or both. It's very obvious. The second type, you have sort of a hidden infinite value that you need to find. So in order to find a vertical asymptote, you need to find places where your denominator of your function is equal to 0 and the numerator is not equal to 0. So in this case, our function is 1 over the square root of 9 minus x squared. Well, the denominator being 0 means that this square root will be 0, so 9 minus x squared is 0. So this means that x squared can be 9, getting ahead of myself. So then x is either positive or negative 3. Negative 3 doesn't matter because that's outside of our range of integration, but positive 3 does matter because that gives us a vertical asymptote. Oops, vertical, there we go. So that means that the upper bound is what is giving us an issue and making this an improper integral. So then the integral from 0 to 3 of 1 over the square root of 9 minus x squared dx. The first thing we need to do is rewrite this in terms of a limit. It's the upper bound that's giving us a problem, so I'm going to rewrite it as b. We are integrating from 0 to b of 1 over the square root of 9 minus x squared dx. Now I left this part blank because I'm going to come back and talk about it now. Our original upper bound of integration was 3, so b is going to be approaching 3. But with these type 2 improper integrals, we don't just have an overall limit. Because of the fact that we have a vertical asymptote, we have to approach 3 from one side. So to figure out which side, it depends on whether you're talking about the upper bound or the lower bound. So think about the fact that you're in the interval from 0 to 3. b is some value in the middle here that you have chosen, and b is going to be approaching 3. Notice that we are to the left of 3 here, so we are approaching 3 from the left. Let me write that better, from the left. So this means that we're going to have a left-sided limit here. Okay, so now we have our limit set up. We need to think about evaluating this integral. Well, if you notice the fact that we have the square root of a squared minus x squared form, this should make you think about a trig substitution. Specifically, we are going to use the substitution x equals a sine theta, where specifically a is equal to 3. So then we need dx to be equal to 3 cosine of theta d theta. I don't really feel like finding new bounds, so I am going to evaluate the indefinite integral separately. Okay, so 1 over the square root of 9 minus x squared dx will be equal to the integral of 1 over the square root of 9 minus 9 sine squared theta. Then we'll have 3 cosine of theta d theta. What's under here? We're going to have 9 times 1 minus sine squared theta. Square root of that, so that's going to be the square root of 9 times cosine squared theta, which will give us 3 cosine theta. But that's in the denominator. We already have a 3 cosine theta in the numerator, so that's all going to cancel. So what we are left with is the integral of d theta, which is just simply theta. Yes, we would need a plus c, but I'm not going to care. That's not going to matter all that much in this problem. Well, theta is equal to, if we go back up here and solve for theta, theta is equal to the inverse sine of x over 3. So we have that this is equal to the inverse sine of x over 3. Before we go anywhere, notice the integral of 1 over the square root of a squared minus x squared dx is equal to the inverse sine of x over a plus c. This is a direct antiderivative, which means you can memorize it. But it is not the easiest to remember. If you do remember it, then you can go straight from 1 over the square root of 9 squared minus x squared to the inverse sine of x over 3. That's perfectly fine. You don't have to show any of this work with the trig substitution. But if you don't remember the direct antiderivative, notice that you can use a trig substitution to get to the same answer. It's just a little bit longer. Okay? So, now that we have our antiderivative, I'm going to take this and plug it back in here with my limit. So, the limit as b approaches 3 from the left of the integral from 0 to b of 1 over the square root of 9 minus x squared dx will equal the limit as b approaches 3 from the left of our antiderivative, inverse sine of x over 3. This gets evaluated at 0 and b. Plugging in our bounds, rewriting our limit as b approaches 3 from the left of the inverse sine of b over 3 minus the inverse sine of 0. It's always good to try direct substitution when you're evaluating a limit. If you did this, you would take 3, plug it in here, divided by 3, you'd get 1, so you'd have the arcsine of 1, which actually is defined. So, inverse sine of 1 minus the inverse sine of 0. The inverse sine of 0, well, that's an angle that gives you a sine value of 0, so that is 0. Inverse sine of 1, that's an angle that gives you a sine value of 1, so that means this is equal to pi over 2. So our final answer then is pi over 2. So the integral from 0 to 3 of 1 over the square root of 9 minus x squared dx is equal to pi over 2.